to come and touch my tablet and then scroll and zoom in and out, you can feel free to use it. I have a question as well, like what you have wrote down was fantastic. Can you give us a copy of that? Well, actually I'm using this software that I write directly to the cloud. So you can only access it if you have got cloud access. So, and then you require password for it, which is my password.
So you can screenshot and send us, ma.
What you can do was my advice that I gave you before. Look at your materials before you come. Okay, and I'm going to give you more materials. There are slides used by Glasgow. They are more related to these materials. Okay. Okay, let's get started. Let's have a look at case 2, where theta is greater than 1. So if zeta is greater than 1, this is the case where we call it a system that is overdamped. Overdamped here means that there's just too much damping. So if there's a lot of damping, then we call it overdamped, too much. Right? Overdamped. And I'll be using that equation star. So I want you to refer back equation star. So I'm going to write it down again so that you can see that equation star. So that one has S minus omega n minus zeta plus square root zeta square minus 1. And S minus omega n minus zeta minus square root zeta minus 1. Right, that was equation star. So this one here, what I'm going to do is that for the case of overdamped, where zeta is greater than 1, it will have the following way of factorization. I'm going to factorize it in the following way, where this denominator, one of it over here, S minus omega n minus zeta plus square root zeta minus 1, and the other one S minus omega n minus zeta minus zeta square minus 1. We can actually split up this denominator in this following way, where this numerator here will be A, that numerator there will be B, and I'm going to find out what will be A and B. In order to find out what is A and B, do you remember the mathematical tool that you would use to do that? That is partial fractions. Right? So using partial fractions. If you're worried that partial fraction has long left you, right? Don't worry, because I'll put some exercises in the Moodle so that you can download it and practice partial fractions.
Here comes your birthday.
So, if I were to use partial fractions, if I were to get that formula, I'm not going to solve it. Right? I'm going to use actually an example to demonstrate that. But over here, because there are a lot of symbols, it gets very involved. So if I'm able to find out what is eventually A and B, then I'll be able to take the inverse of the plus. So I'm going to do the short form for inverse of plus. L minus 1 is inverse of plus. So if I'm able to do that, then my xt, my time response, will be equal to x naught e to the power minus zeta omega nt A e omega n square root zeta square minus 1 t plus b e minus omega n square root zeta square minus 1 t. This one, right? This is the form for overdamped system, where your A and B would have the following form. It will be in this form, 2 zeta square root zeta square minus 1, and B would have this form. This entire part of it is for overdamped system and is provided in the data sheet. So you do not need to memorize this. What you need to know is that for an overdamped system, it's an overdamped system, the expression is given by this. So just now we sketched the form for an underdamped system, how the graph looks like. For an overdamped system, if I were to sketch it, it's going to look like that. It's time again. This is your xt. It's going to look like that, where this value over here is your x0. Right? This top value where it intersects your y-axis. So we can see that there are a few things to take note. First, in this equation here, there's no sine or cosine terms. That means it's a non-oscillatory response. And what you could see as well, there's this exponential. So it's actually a pure exponential decay expression. You can see that it's purely just decay. There's also the kind of like, just call it the overdamped second order differential, second order system. So you can see that this expression over here, right, is always this form here, always this form for the overdamped system. For an underdamped system, just now you have seen the equation, always in that form. That was case 2. Case 3. Case 3, you have zeta that's equal to 1. In this case, we call it the critically damped system. So for a critically damped system, we'll take equation 3. I'll write down equation 3. x0 s plus 2 zeta omega n s squared plus 2 zeta omega n s plus omega n squared. That was your equation 3. Since zeta is equal to 1, and this is a case where we call this critically damped system, that means that zeta term over here, this term, is equal to 1. So what I can do is to substitute that in. So x0 s plus 2 zeta omega n s squared plus 2 omega n s plus omega n squared, where zeta is equal to 1. Okay, zeta is equal to 1.
I found out something. There's something called touch and draw. Okay.
So I can simplify this further. Numerator
So I And
But
actually
this
draw my
will be
screen,
equal
but
to 1 as well.
the accuracy is not
The
there
numerator, this
because
one,
it's not meant for this
equal to
purpose in
1.
the first place. So my stupid pen doesn't work.
This also equal to 1. So that denominator, I can now split it up into the following form. S plus omega n squared. And that numerator, I'll also do something to it. I'll break it down into two terms, where the denominator will be the same. And this numerator, I'm going to keep s plus omega n, because it's s plus 2 omega n, so the other omega n will go to this side, omega n. And what I'm going to do is to have here as 1, and here as 1. Why do I do it in this way? That's because later on I can factorize, I can do an inverse Laplace here. So this numerator and denominator, this can be simplified, so it's 1 over s plus omega n. So I'm going to try to inverse Laplace this following expression. So if you refer to your inverse Laplace formula, let's have a look. 1 over s plus omega n. So 1 is s, is omega. Only 1 is going to be from this. 1 exclamation mark doesn't mean you say 1 louder. 1 is factorial. So factorial, if you have not heard before, if you have 2 factorial, 2 factorial is the same as 2 times 1. 3 factorial, 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, etc. Right? So in our case here, 1 factorial is 1 over s plus omega n to the power of 2, so 1 plus 1. So I'm going to make use of this. Do the inverse Laplace, I'll get this form. Right. The second one, 1 over, I'm talking about the second one. First one, have one at the top. So 1 over s plus omega n. Right. So if I do an inverse Laplace, I get that. So the second one, the first one, that's the second one. So inversing Laplace. Inverse Laplace. You have xt equal to x naught e to the power minus omega nt plus omega nt e to the power minus omega t. So there's a common factor, that is e to the power minus omega nt, 1 plus omega nt. So again, this is your critically n system, and is in your data book as well. So you don't have to memorize this one. So if I were to sketch this, how is it going to look like? Time xt again. So if I were to sketch critically damped, it's going to look something like this. So it will drop very rapidly. right? More rapid than the overdamped case. So this is starting at x0 as well. So there are a few things to note. Again, this term, this expression is a purely exponential one. This is what we call is a critically damped system, and zeta is equal to 1. So that equation does not carry the parameter zeta, right? Because zeta is already equal to 1, so this expression don't have a zeta expression. So this case here, we can find out then what is the critically damped coefficient. Critically damped coefficient, that's called CC, right? Just now zeta is called your damping ratio. I'm talking now about damped coefficient. In this case, the critical one. So we know that zeta is equal to C over 2 square root km. And if zeta is equal to 1, then we can express this form, which is going to be your CC. So CC here will be equal to 2 square root km. So that is your critically damped coefficient. So if I were to re-express this, zeta now becomes C over CC. And this, of course, equal to 1. So if I were to superimpose all these sketches, you can actually find it in your data sheet. So if I show you your data sheet, right over here, the second page of the data sheet. So we can see that the one that's red color, that's the one that's under that.
Thanks.
So that one, you will find that your zeta value is indeed less than 1. So this 0.3 is also less than 1. So if it's 0.3, then it's a black line. And we know that you will oscillate. And over here, I make sure that your graph,
because the screen is not meant for writing.
Frequency or the damp here is tau d equal to 2 pi over omega. So you have the formula.
Daiso $2. Daiso.
If zeta is equal
Because
to
the
1,
screen is not meant for writing, it's just meant for hand motion only. Yeah, the writing is on the pad here. This side. But the thing is, writing on over here, right? The accuracy is very hard to get. Because you are writing here, but you are looking at the screen at the front. Right?
That is a case of overlap. So this is superimposing all the graphs together. So you can see which one is it that's oscillatory and which one is not oscillatory.
Writing. Okay, is that writing larger?
Because you know what? I put it to minimum. Oh my god.
So
This one was like writing
it's actually
100%.
quite boring to just look at equations, isn't it? So why not I do a demonstration?
Yeah, just stick to it lah. Adjust here, adjust there.
I think I just stick to this way.
So what I have over here.
Oh, actually, you should write at minimum first.
What I have over here is
high wind speed. So I bought this from Dyson. And the idea is that I want to have quite a significant amount of damping. So if I were to release this, you can see that, yeah, there's quite a significant amount of damping. But then some of you will be wondering, you'll be thinking, hey Rob, wait a minute. Just now you did show a case of a spring without any damper. I was using a cardboard for a damper. Don't you think the cardboard is going to add in a little bit more weight to your spring system? Although it's also damping, but that cardboard will come with a certain weight. Wouldn't that weight change that oscillatory frequency? So is it caused by damping or is it caused by the weight of that object? That's fine. I bought one more. Another one. So what I'm going to show you is that as I drop these two windscreens are of the same weight. One can feel damping, and the other one is straight vertically down.
This is every
It doesn't
distance
have that
there.
much damping. So I'm taking weight out of my equation. It's not going to be influenced by weight anymore, since these two are of the same weight. So if I drop these two, if what we have seen before just now says that the one without damping is going to oscillate faster, the one with damping is going to oscillate slower, then you'll be correct in this case. So I need something to hang on to this before I release. So, wait. I brought something here.
No wonder he has to come early, yeah.
It's an extend.
Sunshine, 9 o'clock.
So what I'm going to do is hook this up. Okay, this one over here. Same mass. This one is going to be over here. They're going to be quite close to each other, so I hope you don't bang against each other. So what I'm going to do is to perturb these two
But no
systems.
battery, I pass you the battery.
So I'm going to perturb this. Pull it down, and then pull this down at the same distance as well. So if I were to release it, then this side over here is going to oscillate at a higher frequency. So let's see. 3, 2, 1. It's at a higher frequency. And this one was oscillating, but yes, already damped. It was oscillating at a lower frequency. So this shows that it's indeed
The button would not working.
not under the influence of weight, but because of damping. So the damp frequency is actually lower. How about the case where we have overdamp? Because what we can see over here, if I were to oscillate this, yeah, it kind of like go up, come down,
The button
up.
spring spoil. But when
So this kind of response
all
is
the
an
way
underdamped response.
all the way.
So what I'm interested in is what are the case of overdamp response? Too much damping.
Oh my
So much damping
gosh.
that you will follow the behavior that
Always
caused this
I
shock.
know that's you.
So what I'm going to do is to take this up.
Give me what you did.
Okay, I show you. Okay, give me a math question.
And after I took it up, then
Give me a
I'm
math
going to put it
Next question.
into a damper.
Like,
There's so much damping.
Okay,
So not this damper anymore. I'm going to use a damper that's big. How big? This big.
now I know what he does for a car.
Actually, it's going to give me so much damping that I can start to consider if this system here is under the overdamp case. That is underdamped. You can see that it's oscillating. The overdamp case shows that from the equation, it's not going to oscillate. Correct. That's E. That's the law of damping. So if I were to fix my spring up, actually my water calculator. So I'm going to put these over here. And as you can see, it is flat. Yeah. So what I'm going to do is that I'm going to show this first, and you're going to remember how
There's no solution.
I'm going to show this one first. Right, the oscillates that way. Remember that one?
Okay, plot graph.
And now, what I'm going to do is the oscillate, the over-damped case. Yeah? Over-damped case. So I'm going to pull it down. Now, it will kind of tilt a little bit, right? But what I want you to focus is this point over here. This point over here. Does it oscillate? It kind of float up. You can see that there's a lot more damping. It's actually close to the case where it's overdamped. And if it's overdamped, then there will not be any oscillatory response. So it's a case of an overdamped.
It's fantastic.
With so many equations, it's actually easier if I were to show you an example. So let's have a look at an example. The work example
Circle the part of the equation that you want to fix.
So if you look at your data, your board example, these are example, and I'm gonna make use of this figure over here.
Oh,
So I'll go and
so
cut
cool! This is so
that
freaking
figure.
cool.
The figure is over here. Copy it, and I'll plug it here. So first thing first, if you're dealing with a system that's that way, what comes to your mind immediately is that this is actually a rotary system. Why is this important? If you don't think that way, then you start to use x dot, x dot dot. These are wrong. If it's a rotary system, you should be saying feeder, feeder dot, feeder dot dot. So if you were to use x dot and x dot dot that's provided in your data sheet, then you'll lose some marks because you didn't recognize that this is a rotary system. Why rotary? Because the pivot over here, and the only way for this mass to move is rotation. Right? Unlike the case that we had before, the spring is vertically down. So that one is a translational system. A translational system, you'll be using x dot and x dot dot and x. Yeah. So the equation asks us to find out the equation of motion. If you have not read the question, it's asking us to find out in this system, what is the equation of motion? What's the natural frequency? What's the critical damping coefficient? What is your damping ratio? And what is your natural frequency? Right, in that first paragraph. So in order to find out all those, first thing first is to sketch the free body diagram at BD, free body diagram. So the free body diagram we're going to sketch for the case where it's for static. So see how I'm going to sketch. Since it's not moving, static, it's going to go straight. And there's going to be this mass over here. The free body diagram of that is that it's a point mass, so you'll have mg. my datum x is taken downward in that way. I think in your figure, the theta is written in that way. And this spring force that's exerted at the top, somewhere at the midpoint, here, it's actually a distance a away. So at the distance a, that force that's exerted at that point, let's have a look. Do you think this spring over here will be under extension or compression? Extension. So you got to sketch that spring, extension in that way. So the other two sides of it, equal and opposite force. This part here, the arrow is what I want. This direction should be pointing up. Okay. Notice very carefully how I establish my free body diagram. You have to go through these steps. So that spring force, we know is K delta. We have seen that in earlier examples. If you're not familiar with what I'm talking now, like when I say earlier example, if you're wondering earlier example, then please go back home today, look at yourself in the mirror and say, I should have done better. Because it's indeed covered in earlier lectures, and if you're not up to that, then that means you are one step behind. Don't leave yourself too many steps behind, or else subsequent lectures you would have difficulty in understanding. You see it in your hands.
That's so harsh.
So the other thing that I want to point out is that there's actually this damper underneath. And the important part is that since we're talking about static condition, note there's no static damping force. So please don't add the static damping force over there. There isn't a damping force in static condition. There's only damping force coming about from dynamic condition, not static. So there isn't this. So if I now were to sum up moments around point O, this is my point O, in static condition is equal to 0. Please don't sum up the forces because it's a rotating system, right? If it's a linearly translation motion, then you sum up forces. But in this case, it's summing up the moments. So moments, as you know, is force multiplied by perpendicular distance. So that moment, I can take this one over here, mg, that's the force, multiplied by the distance. So in this case, in this figure over here, this is L. This perpendicular distance, L. So mg, L. And this mgl moment is in the direction of my convention, so it's positive vector. The other force, the other moment comes about from the spring force and is in the opposite direction of my convention x because it's rotating in a counterclockwise direction. This mg is rotating in clockwise direction. So because anti-clockwise, so minus, because it's against our convention, and k delta is the force multiplied by the perpendicular distance, that's k. So the whole thing equal to 0. You'll find that in the later part of the topics, after this free vibration, so now there is spring, and then now there's damper, and then it's perturbed and freely oscillating. This is called free vibration. There are going to be 4 topics. This is the first topic. First topic, I will still be showing you the static condition. In the second topic onward, I will start to jump into the dynamics straight because you need to speed up. You need to be able to see your static condition already and then go straight into your dynamic. Don't worry, I'll be there. So your dynamic condition, if you were to notice, I've also cut down on the word condition because I want to save time. Because in exam, you really have very little time. So I want to teach you some of these little things that you can have so as to save time. Under your dynamic condition, again, you need to sketch your dynamic condition figure. See how I sketch. There will be that dotted line to show that this was the axis that we deflected. And how we deflected is that it used to be over here, and now it swings downward. So your mg force still stays over there. Your spring force, which is going to be over here,
Can't be helped.
in the dynamic condition, your spring force, as you know, is K delta plus X. But in this case, that X here was a result of this displacement. So this displacement over here is actually A sine theta, where this is your theta. So that force will be delta plus A sine theta. And this distance over here, hence, will be your A cosine theta. And this entire length, from here to here, that will be L cosine theta. There's another force in the dynamic condition, that is your damping force. So if you look at your damper, do you think this damper is under compression or extension? Compression. So if I were to sketch the damper, I will sketch the arrow that's compressing it. So the equal and opposite force, where your beam is at the top, that arrow will be pointing upward in that case. Yeah. So the damping force over here, it will be F equal to C x dot. That's the one that you heard before. But we can't use x dot in our case because x dot is for linearly linear motion, linearly translational motion. This is a rotary one. So what we need to do is that the velocity of the attachment point of this damper, right, the velocity at that point, that x dot over there is actually equal to a theta dot. How do I get that one? That's because in a rotary motion, you have this is the center of a circle. If you have a rotary motion, that point that's rotating, that velocity, this point, the velocity, is actually equal to r omega, where r is this radius, and omega is your angular velocity. So in the case over here, that angular, that tangential velocity, that will be equal to r omega, and in my case, this r here, with respect to this pivot point O, this is actually a instead of r, because that's the distance from here to here. This is a, and then omega here will be my theta dot. So I can't write C x dot. It's actually C a theta dot. Yeah. So that's to say, when you have a rotary system, then that damping force is C radius theta dot. Yeah. Note this a here is not acceleration. This a is the distance of this length from the pivot point to where the point where the damper is acting on the beam. So now we can have the expression summing up moment around point O, and because it's a dynamic case, it's not equal to 0, but I naught theta dot dot. Always that case. So summing up the moments, we have quite a few forces, mg one of it, damping force and the spring force. Mg is the force that's along our convention, so it will rotate clockwise, so it's a positive value for the moment. The damping force and the spring force is in the counterclockwise, so both of them will be in the negative moment. It will give us a negative moment. So first one, mg, force multiplied by distance, perpendicular distance, that's L cosine theta. The second one, maybe let's look at this damping force. It's in the opposite direction, so minus. Force will be CA theta dot multiplied by perpendicular distance. That perpendicular distance is A cosine theta. Yeah. Force multiplied by distance. Force and perpendicular distance. Next one, the spring force is also in the opposite direction to our convention. So minus K sigma plus A sine theta. This is force multiplied by perpendicular distance, which is also A cosine theta. This whole thing equal to I naught theta dot dot. This I naught over here is our moment of inertia. So moment of inertia for a point mass, we have seen in the previous class before, is mass of that point mass multiplied by the distance from the pivot point. So in this case, the distance is L, and then take a square. Right? In your data sheet, you'll find that it's written as mr squared, where r is the distance from the point mass to the pivot point. So if you're not familiar with this, there's also last week's example. You can have a look at that as well. So the next thing to do is that we need to assume for small angle theta, the sine theta is approximately equal to theta, cosine theta is approximately equal to 1. So what that means is that this cosine theta over here is a block approximately equal to 1, approximately equal to 1. This one here approximately equal to theta, approximately equal to 1. So I'll tidy it up a little bit. That will be mgl minus c, there are two a's there, a squared, theta dot, minus k, that is delta plus a theta, multiplied by a, equal to ml squared, theta dot dot. So I can see that there's mgl k delta a, which looks familiar because I have at the top mgl minus k delta a equal to 0. So that means I can simplify it. mgl minus k delta a minus ca squared theta dot minus k a squared theta equal to ml squared theta dot dot. This term here, because of the static condition, is equal to 0. So whatever that's left, let me do a bit of adjustments. The adjustments of ml squared theta dot dot plus CA squared theta dot plus KA squared theta equal to 0. Just a bit of rearrangement. I'll divide it throughout by ML squared. Divide throughout. So I have CA squared over ML squared. KA squared over ML squared equal to 0. So this can be a little bit more simplified. The square and the square, I'll take it together. And the same for that term. Over L squared theta equal to 0. So that is my equation of motion. Now for a damped, and I know it's a damped second order system. For this damped second order system, why do I know that it's damped? Because I could see that in the figure, that's a damper. We know that its general form is this. General form is from your data sheet. X dot dot plus 2 theta omega n x dot plus omega n squared x equal to 0. So omega n, we've seen before, is actually this term over here. So they must be equal to each other. So what that means is omega n is